Today we're going to go over R, how we can compute different measures of variability, z-scores, and z-tests. Alright, so first let's grab your data. If you don't have it already, grab your data at this website, and we'll use this to do all of our measures of variability. So put this in your working directory, and then get into R and set your working directory appropriately. This is the same data that we used last time, so hopefully you guys all still have it. Everyone has it? All of you. All right. Now that we all have it, we can do some very simple measures of variability. All right. One measure that we talked about was the maximum. We can use max ages. So go ahead and type this. Holler out the answer when you get it.
56.
56 point something. 0.93?
Yeah.
Something else? Good. All right. Minimum was also something we were interested in. Try min. Ages.
22.71.
22.79. If I rounded it to that point, it'd be that. Good. How about range? If I want the range, what do you think I'd use? Range. Go ahead, try range. Ages. You get the minimum and the maximum, right? But we said that the range, it's not the minimum and the maximum, it's the maximum minus the minimum. So if you want to find the range as we define it, you're actually going to need to take max ages minus min ages, and that will give you the range. So how do you do that? 34 point something. Groovy? Alright, we already tried range ages. Now let's do some quartiles. Now, we talked about a function that can give us any quintile that we're interested in. And a quartile is just a special type of quintile. So the first quartile, we're going to say, I'm sorry, not quintile, quantile. This is quantile ages, and then we want to say 0.25. That will give us the value that separates ages into 25% and 75%. 33 and some change. All right, so that's the first quartile. Now do the second quantile or quartile. That's the median. We can do this, or we can just type in median ages. Both of those should give you exactly the same answer. 0.25. This is saying we want the value that separates ages into 25% and 75%. So give us the value that gives us the bottom 25%. Okay? Here we're saying the bottom 50%. And for the third quartile, we will use 75% or 0.75. So quantile ages 0.75 is. And you don't have to keep retyping in these. You can just use the up arrow and change the value. 45 isn't changed. Great. How about this? Type in summary ages. Don't type in the question mark after it. Just summary ages.
Oh, medium first.
Wow! Awesome. 7,900. Oh, you did a sum. Not sum ages, summary ages. Gotta be careful. Sum does not equal summary. Does not equal summarize. Summary gives you the maximum, the minimum, the median, the mean, the first quartile, and the third quartile. So, if you're doing homework, and I ask you, like, what's the maximum? And then you see another question like, what's the first quartile? You might think, oh, I think he's just going to ask us for a whole bunch of the stuff that's provided by summary. So just do the summary once and then copy and paste the appropriate values. So that's sweet, really easy. Okay, now we can graph some of that data that we had. So if we took the maximum and the minimum and the first quartile and the third quartile and the median, we could produce a box plot. So do box plot ages. Should get something that looks like this without the labels. Groovy? Now you can make your own box plots. Yay! It's so easy. R is so easy. once you know how to set the working directory and save the file and load the file. Okay. All right, variance. Now we talked about the variance. What was our formula for the variance? Does anyone remember? Variance wasn't sigma, it was something else. Sigma.
X minus u. X minus mean. Over.
Divided by sigma.
Sigma divided by
Is it Z?
No. No, this is wrong. What will this give us? That's a z-score.
Yes.
I don't want to know the formula for z-score, I want to know the formula for variance. And variance is not sigma. Variance is something else. So what is variance? It's not sigma, it's sigma squared. Sigma squared equals
square root of the square root of x minus n.
x minus n, the square root of this?
N, the mean.
Not m, but mu. But yeah.
Okay, over divided by n.
Divided by n.
Root square, square, not the root. Square.
We need this symbol.
We need this symbol. We need the sum symbol. Okay, where do we need the sum symbol? Actually, this is wrong. So let's get rid of that.
Sum is
Sum is 8 minus. And the
Here's the square, right? That's it. Great. Okay, so there's our formula for it. So with R, we can do this. Hold on. Well, let's do this in an easier way in just a minute. Don't worry about this. But notice what I've done. I have used some parentheses here. The first sum, okay, so this parenthesis connects to this. So I'm taking the sum of ages, that's each score in age, minus the mean of ages, and I'm squaring it, right? Now, that's the top part, and on the bottom part I have length of ages, which just tells me the number of ages that I have. It equals this. We'll come back to this in just a second. Come back to that in just a second too. Okay, this is like a really long formula. And you could easily make some mistakes. So let's try to do something else. Let's create a new variable called n. N equals length ages. So go ahead, type that in, and then tell me what n equals when you've got it done. 50? You should have 200.
200.
Oh, you just wrote like n equals 50? Don't write n equals 50, write n equals length ages. Because 50 does not equal length ages. We have 200 ages. Alright, so then you can do diffs. Right? To get the variance, what we're doing is we're squaring deviations, or we're squaring differences. So just make a new variable instead of ages, call it diffs. Diffs equal ages minus mean ages. Say what? We're subtracting a mean from every single age when we do this. Go ahead and type in some diffs to see what you get. What should you get? The sum of different scores should equal... Does anyone know what they should equal before you type it in? You get lots of numbers, but they're all different scores from the mean. And what do we know about the sum of differences from the mean? What should they equal? 0. So type sum diffs. You should get 0. Or maybe something that says like some number times e to the negative like 16, which basically means 0, but R, there's some rounding error in there. That's why you don't get exactly 0. Okay, now what we want here, so we just calculated diffs, right? But we want the squared diffs. So then all we have to do if we wanted to do that would just be to say diffs squared. So if we want the variance, that's sigma squared. So the variance is just going to be the sum of the squared differences divided by n. So go ahead and type sig2 equals sum diffs.
6 squared is the first one 6 squared.
The first one 6 squared. And what?
Sigma squared.
No, this is sig2. I've named it sig2. It's the variance. I've just created a name that I'm going to store the variance in. I didn't want to say sig raised to the 2 because then R would say error. We don't know what sig is. No one has defined sig. 62 something?
Yes.
If you got 6,000 something, you've probably done something wrong. Okay, so sig equals sum
62.
diff. Haha, yeah, you didn't type in diff, you typed in diff. And also, it's not divided by 2, it's divided by n. So now, if you look at sig2, say I2. Haha. Okay, does everyone have something like 62 something? Okay, yes. Okay, so what does sig2 mean? If you type in sig2, you get this value of 62 something. What is that value? It's the square of sigma, or it's sigma squared, which is
Variance.
variance. That's variance. Okay? So, if we go back, I said it was roughly 62.3. Is this the value that you guys got?
Yeah.
Good. Try this. Try var ages. 62. This is different. var calculates variance, but it's calculating a different type of variance than what we want right now. After the exam, we'll talk about what this is calculating, and then we'll use this one a whole lot. But for right now, the variance that we're calculating, this will not give us the right answer. So you need to compute it this way, or using the easier way, where you just sort of group things together. Okay, so the standard deviation. All we need to do now for the standard deviation is just take the square root of everything, right?
Yeah.
So sigma is equal to the square root of that. So if you take the square root of sig2, you should get the answer. So let's see how we can take the square root in R. Try this. SQRT sig2.
7 something.
7.89
Yeah.
approximately. Now if you type in SD ages, SD is the formula for standard deviation, but this is different than what we're calculating right now. It's a little bit bigger. We will be using this in the future, but not right now. So if I ask you to calculate the variance or standard deviation for the homework or on the first exam, you're going to want to use the formulas that I gave you, the ones where you are summing up everything and dividing by n. Okay, so that's it. Cool. Now you guys know how to get the maximum, the minimum, the median,
Yeah.
the variance, the standard deviation. Sweet. Let's move on to z-scores. So we had two different formulas, right? For one score, what was our formula for z? This is the formula that someone earlier gave me for variance. X minus the mean over
Sigma divided by n.
over sigma.
Divided by square root L.
Wow, divided by the square root of it. That's awesome. I'm really impressed that you guys remembered that formula, because the formula that I gave you guys for just one score was this. The formula for the mean of n scores is that. Now, what I was going to do, I was going to tell you that these are equivalent and tell you to remember this one, because this one will always work. So let's see why they'll always work. So, shoot. There is our bigger formula. Now, when n equals 1, what will the mean of 1x be? So, the mean, right? So, the mean of x, this is just going to equal the sum of all of our x's over n. But we only have 1x, right? So, what does that equal? X plus, well, there's no others. X over what?
1.
X over 1. X over 1 equals,
And x.
x over 1 does not equal n. X over 1
X.
equals x. Yes. So when n equals 1, the mean of one thing, well, that's just that one thing. So, cool. Now, how about for that bottom term? Now, for the bottom term, we have the sigma, or the standard deviation for the population, divided by the square root of n. Now, when n equals 1, what does that equal? Sigma. Sigma divided by the square root of 1 equals sigma divided by 1, which equals sigma. So, if you're going to memorize the formula, just one, memorize this one. And then you know, well, you can calculate. Square root of 1, oh, that's 1, it's just the same thing. All right. So, let's calculate z-scores for ages. So, how are we going to do this?
We can use.
We need, yeah?
We can use the previous one. We type it and like sigma and sum of difference.
And we find
No.
So before we had something called diffs, right? And the diffs was this part up there,
Yeah.
right? For one individual score. So all we need to do is just divide each of those diffs by the standard deviation, right? So we need the scores. We have the scores. Those are ages. We need the mean. We've got the mean. It's mean ages. We need the standard deviation. We already calculated that. We call that sig, right? So z's equals this, or if you want to simplify it, z's just equals diffs divided by sig. So go ahead and type in diffs divided by sig. Z's equal diffs divided by sig. So again, you're going to have like 200 numbers,
Yeah.
right? Why don't you do a summary of z's? So when we did the summary of ages, we had like, I forget what the maximum and the minimum were, but they were like 80 something, 60 something, I don't know. But they were like normal ages. Now what is the maximum and minimum for the z's? Minus 2 something, and
Minus 6 something.
minus 6 something.
Yeah.
We have an age that's 6 standard deviations away?
No.
That sounds odd. I need to do this in a while.
Okay. Sum of this.
Okay, so diffs equals ages minus mean ages. So z's equals diffs divided by, oh, I didn't type in my sigma.
This.
Sorry. Sig equals, square root sum diffs squared divided by length ages, right? Is that right? All right, so z's diffs divided by sig, summary z's.
Summary.
Cool. So our biggest one is negative our smallest one is negative 2.14, biggest one is positive 2.18. That means our smallest one is negative, is 2 standard deviations and some change beneath the mean. Our biggest one is plus 2 standard deviations above the mean. All right. The mean, oh my goodness, the mean of the z-scores is just 0. This will always be the case. The mean of z-scores is 0. Why? Well, because the sum of z-scores, this is just a sum of differences divided by something. And we know that the sum of differences is always 0. So if you want to check and make sure that your z's have been done correctly, you can do something like this and look to see whether the mean is 0. It should be 0, or very, very close to, like some number times e to the negative 10, 15, something. All right, groovy. Now let's compare the distributions. So I created a histogram of the ages. I used special breaks because R, when it broke it down automatically, it gave me 8 for ages, and it gave me 10 for the z-scores. So I wanted to be able to directly compare z-scores to ages, so I used my own breaks. You can download the R code that I used for this class and see exactly how I did that if you're really interested. Okay, so here's the histogram of ages. If I plot the z-scores with those same, the same number of intervals, I get something like that. Looking at these two, what can you tell me? They have exactly, basically, the same shape. The scale is a bit different, right? This goes 20 to 60, this one goes, what would the equivalent be? I don't know, it would be 2 point something to 2 point whatever. So their range is different, but when we scale in appropriately, we have exactly the same shape. This is really important. Taking z-scores does not make a distribution normal. Some people think incorrectly that, oh, if we don't have a normal distribution, all we have to do is just take the z-scores and then we'll get a normal distribution. That's wrong. Taking the z-scores will give you back the same distribution shape that you had originally. Now, why is this important? It's important because the z-tests that we discussed are based on a normal distribution. This means that if the distribution isn't normal or close enough to normal, we'll talk about what that means later, then we can't use the z-test. So for the homework, like you may have noticed last time, I said like assume a normal distribution or something like this. This is why. Because if we don't have this assumption, we can't assume that, then the p-values that we come up and the cutoffs that we come up with aren't going to be the right ones. Okay, so I was thinking about how, things have really changed so much. And I was thinking about, in the future, are people even going to teach z-tests? Because z-tests were really, really important back before people had computers to calculate probabilities down to, as much precision as you want. Now, when people used to use tables, z-scores, they were critical because you don't want to have a table for every combination of some mean in sigma, right? So you have IQs. They have a mean of 100 and a standard deviation of 15. If you wanted to calculate the probabilities for those, you would need a table with a mean of 100 and a standard deviation of 15. If you had a different distribution, mean 8, standard deviation 2, you need a different table for that. Or, if those things are all normally distributed, if we take the z-scores, then we have the standardized measure, right? So instead of needing an infinite number of tables, the z-scores, you just need one table, right? For a mean of 0 and a standard deviation of 1. This would allow you to look at any normally distributed data set. And after you figure out, the z-scores for those, then you can just look at the table of the z-values. This is awesome. But now we have something even more awesome. We have R. So we're going to skip a lot of the calculating z's when we actually are doing our z-tests. Now, we saw that some critical values for z-scores, Or we saw some of these last class, right? We talked about plus or minus 1.96, we talked about plus or minus 2.58, we talked about some other values as well, right? Now, these values are in terms of standard deviations, right? Not in terms of ages, or in terms of centimeters, or in terms of decimals. They're in terms of standard deviations. This means that for any normal distribution, the probabilities that are based on these standard deviations are identical. So the probability of observing something one standard deviation away from the mean with a mean of 100 and a standard deviation of 10 is exactly the same as the probability of observing something one standard deviation away from the mean when the mean is 8 and the standard deviation is 2. Alright, so a square that falls 3 standard deviations away, regardless of what actual mu and sigma r, the mean and standard deviation are going to have exactly the same p-value if the distribution is normal. We've got to have it. Okay, so now we don't need to calculate z-values. We can find our answers directly. We're going to use some different functions. So we are going to use, actually we're not really going to use r norm much, but it's important for you to know what it is. What is r norm? What do you think? We talked about r binom before. You guys remember what our binom did?
Experiment. Just calculate one result.
Yeah, with our binom, we were able to tell it like how many times we wanted it to flip a coin or do any type of binomial experiment. With our norm, we're going to tell it to pick out randomly so many numbers out of some normal distribution. So, given a normal distribution with this mean and this standard deviation, I want 100 values, 100 random values for that. This is like random sampling. So our norm is going to randomly sample from a normal distribution. How about D norm? Density. This is going to give us probability densities. So with D binom, we actually had probability masses here, where we actually have real probability densities. So that's D norm. P norm. It's cumulative probability, right? Basically what Q binom, I'm sorry, not Q binom, what P binom did was it added up all of the probability masses for some number of successes or successes fewer than that, right? So P norm is going to basically do the same thing. It's going to calculate the cumulative probability mass for a value from the normal distribution. So if I said, you know, what's the probability of observing an IQ of 100, given a mean of 100 and a standard deviation of 15, it would tell me what that probability is. So it would tell me the probability for that 100, probability for anything below that, 99, 98, 97. But this is now not some binomial thing where we can only observe like 99 or 100 successes. We could observe a test score of like 99.5, 99.23, right? This is a continuous distribution. And Q norm. Okay, what did Q binom do? Told us about quantiles. So with Q binom, it would tell us what value cuts off particular percentages of scores. Q norm is going to do exactly the same thing. So it'll tell us the desired quantile for a normal distribution. Now, all of these things depend on the normal parameters. When we were talking about the binomial, we had to know what P success was, and we had to know how many observations we had. For the normal, we have to know two things. They're different than what we needed to know for the binomial. What are these two things that we have to know?
Sample size?
No, we don't need to know sample size.
The mean.
We need to know the mean of the population, which we might not always have, and we'll see how we can deal with that later. So we need to know the mean. What else do we need?
More? More?
One?
The mode.
The mode? No. We don't need the mode. X? No.
Variance.
Standard deviation. We need the standard deviation. Remember last class how I said that the normal distribution depended on the mean and the standard deviation? And then we looked at several different normal distributions with different means and standard deviations, and we saw how it shifted the things around or increased the height of the peak, but when you zoomed in at the appropriate scale, it looked exactly the same. So for the normal distribution, we're going to have to provide it with the mean and the standard deviation. We're going to have to provide these parameters to each of those equations. To R norm, to P norm, D norm, Q norm, whatever. We're going to have to give them these parameters. Where do we get these? Well, just like when we were doing the binomial tests, our null hypothesis told us what these parameters were, right? Or the alternative when we were looking for things like beta or power. So similarly, these parameters are going to be given to us by the null hypothesis or by some specific alternative hypothesis. Okay, let's first talk about finding critical values using Q norm. So, Q norm, what does it do? It tells us what percent of scores fall at, or actually it doesn't tell us what percent of scores fall at or below some score. It tells us what score some percent of scores fall at or below. I sort of phrased that wrong. Basically, it tells us the score that has the cumulative probability of whatever we give it. Now, when we were doing the binomial, remember I had these crazy rules. So for the upper critical value, you want to add 1. For the lower critical value, you need to compare it versus b binomial. We're not going to have to do any of this. So we can use these quintiles directly. And if you want to understand why, come to my office hours. It involves calculus. I could explain it without calculus, but I'm not going to spend the time in this class doing that. So if you're really interested in why, come to my office hours. All right. So let's say we want to know what value cuts off the top 5% of scores in a normal distribution where mean equals 15 and standard deviation equals 3. How can we get this? Type in question mark Q norm. All right, so Q norm, P, mean, standard deviation. Mean, standard deviation, these are the things that we are going to be providing. These are the parameters that we're going to use. So P, what's this? This is the percent that we're interested in cutting off, okay? So if we go back to our slide, I said, what value cuts off the top 5% of scores with that mean and that standard deviation? So, what do you think we're going to use? We're going to use Q norm. Q norm what? First thing was P, probability.
0.05?
0.5, no.
0.05.
0.05, that's actually farther away from the true answer, but it makes more sense.
0.1.
No. We want the top 5% of scores. Right now, Q norm is going to tell us a score that cuts off a cumulative probability. Now, we don't want the cumulative probability to be 0.05. That will tell us the lower.
0.95.
Yeah, we want 0.95. Right? If we imagine our distribution, we want the top 5%, right? But if we say Q norm 0.05, what we're actually getting would be this. But we don't want that. We want this. Now, Q norm 0.95 is actually going to give us that. So how can we get what we want? Actually, hold off on that for a minute. This has more to do with p-values as opposed to finding the critical values. The right answer is Q norm 0.95, 15, 3. Do it.
It's 90
Why
something.
don't we use the mean is 0 and
Well,
SD is 1. It is given
hold off on that for just a second. I want to make sure everyone gets this. What is it?
99.9.
So it's 19.93? Something like that? Good. So, why didn't we use 0 and 1? Let's do this. Let's use 0 and 1. This is a good question. Go back up, type in Q norm 0.95, 0, 1.
1.6.
1.6. Give me one more decimal point.
4.
4. Oh, that's just that value that we saw from the previous class. Right? Cool. All right, so 1.64. Now I said that any normal distribution, if we know how many standard deviations away something is, it will cut off exactly the same amount of the probability mass. It will cut off exactly the same percentage scores. So if our true mu was 15 and our true standard deviation was 3, and this was some z-score, right, a critical z-score, and we wanted to go from a z-score back to a raw score, what do we need to do? So we had a formula, right? So we said z is equal to x minus mu over sigma, and we said, okay, maybe we want to know what x is. So what is x? X is equal to
the cross sigma and multiple
Plus
mean.
plus
Mean.
mu, right? Great. Okay, so now we figured out that the Q norm for 0.9501 equals this. Now, what we can do is we can say, okay, x equals 1.64 times the standard deviation we're interested in, 3 plus 15. What does that give you?
So your answer is 18.93.
Yeah, this is this. So, if we were using tables, we would want to calculate the z-score. We would want to do it with the z-scores. But since we have R, we don't need to calculate z-scores in the middle. We can directly solve for the critical values for our original distributions. So this is pretty cool. Okay, so another example. So IQs are normally distributed with mu 100 or mean 100 and standard deviation 15. Actually, it depends on which measure of IQs you're using, but the most popular ones have these parameters. So now we can ask the questions of, do Shahir's students have that same mean? Does the average Shahir student have an IQ of 100? Is the average Shahir student smarter or less smart? Okay? They have a higher or lower IQ. Actually, you can question whether or not IQ actually indicates smartness, but that's a different question. So our null hypothesis is this, right? If this is the population mean, if we want to see if our students are different from that mean, then our null hypothesis is a hypothesis of no difference. The mean of the Shahir students is going to be equal to the population. Now, how many tails are we interested in for this question? 2, right? So we have the distribution, 100, and we're interested if Shahir students are above or below the mean, right? So, we've got 2 tails. Let's say we have a sample size of 36. Say that our sample mean was 96. Uh-oh. What are the critical values where alpha equals 0.01?
We're gonna just do the same.
We can do the same.
0.01 is equals, no, wait, x equals to 0.01 multiplied by 56 plus 96. Because you're gonna give us.
Okay, but we don't just say 0.01, right? We need the critical value for that. Right, so before, when we use the Q norm for the normal, or for the standard normal distribution, we set a Q norm for something for 0, 1. Right? But I said we actually didn't need to use 0, 1. We could just use the original mean and standard deviation if we knew them, because we have art, we don't have to look at tables. So we're going to use Q norm. Now we have two tails, right? So we're going to need to do this twice. So for the lower tail, Q norm what? What goes in there? Well, we should know two of the parameters already. Right? We already have the mean and the standard deviation. Right? 0.0. No? What's our alpha?
9.
0.005, right? What? What? Why is it 0.005? Why isn't it 0.01? Because it's two tails. Our alpha, we want our alpha to be 0.01. So if we're looking at a two-tailed test, we're taking half of the alpha and putting it in one tail, and the other half and putting that in the other tail, right? Okay. This is very close to what we're going to do. There's one problem with this. Does anyone know what the problem is? Besides me. Remember when we talked about our formula for z-scores?
Yeah.
And I asked what is it, and people actually gave me the formula for the mean. And what was that bottom part? It wasn't the standard deviation, it was something else. It was standard deviation divided by square root of n. Huh. So this, the 15, that's this. But we have a sample size of 36. So we want that, or if we simplify, 6. That will give us what we're looking for. So we need to be careful when you're doing these types of tests. So we had a sample size of 36. So yeah, good. That's it. Sweet. So our sample mean was 96. What do we do? So a lot of times it's really useful to draw out the distributions and think, right? So this is the mean was 100. Our lower critical value was 93.6 approximately. Our upper critical value was 106.4 approximately. Where does 96 fall? Well, 96 falls like about there. Now, we're going to reject if the null, or not if the null, we're going to reject if the value that we observe falls in this region or falls in this region here. Does that fall in either of those regions? No. What do we do? Fail. Reject. Beautiful. What's the p-value? How do we do this? Okay, here's where that thing comes in. So we have some normal distribution, and we said that we got a 9.6. And the p-value is going to depend on what type of tails you're using. This is a two-tailed test, right? So we want to know the probability for anything as or more extreme than this. So we're going to add up the probabilities of this and anything more extreme, which would be over here. But what is as extreme as this? We're interested in both tails, so as extreme also includes this tail as well, right? Well, as extreme would be, so that's 6 beneath the mean, so as extreme would be 106, right? And everything above that, right? Now we know some things about the normal distribution. We know that it is symmetric. We know that it is unimodal, where the mode equals the median equals the mean. So it's not too difficult to find the p-values. So what we can do is use this. 2 times p norm 96, 100, 15 sixths. Now what does that tell us? Well, this part here, just the p norm, that tells us the cumulative probability of 96, or the probability of observing a score of 96 or less, right? So this part here, this tells us this, okay? So times 2. Why did we do the times 2? To get this other part as well, right? Okay. Go ahead and do this. 0.109? Oh, weird. I don't have it. So that would be its p-value. What if our observation was above the mean? If our observation was above the mean, let's say instead of observing 96, we observed 106, right? If we observed 106, p norm for the 106 would tell us this, right? The probabilities of everything up to that point. But we don't want to know the probabilities of everything up to that point. We want to know the probabilities of that or more, right? We want to know this. So how can we get this?
1 minus.
1 minus this, right? Because the sum of all the probabilities there add up to 1. So we can just use 1 minus that p norm instead of p norm. And then if it were two-tailed, again, we'd multiply that whole thing by 2. All right, so what if the null hypothesis was that, sorry, this should be x bar, that the sample mean is greater than or equal to 100. So here's our distribution again. How many tails are we interested in here? We're only interested in 1 tail. Now, which tail are we interested in? Well, we said the null is that it's equal or greater than, right? So we are not interested in this side. We're only going to reject if it's on this side, right? If it's enough on this side. So we had 96. What's the p-value of 96 for this hypothesis? Yeah, we don't need this 2 here, because we're only considering this tail. oh, there's one other thing. So we said that alpha was 0.01, right? Now before we took our alpha and we put it on both sides. Now here, since this is a 1-tailed test, where are we going to put our alpha? We're going to put all of our alpha over here, right? So to figure out our new critical value, lower Q norm, for our new alpha, we don't divide it in half here because we're only interested in 1 tail. We're using 0.01 instead of 0.99 because we're interested in the lower tail, right? If we're interested in the upper tail, if this instead said x greater than or equal to, then this would be 0.99, but it's not. Okay, so if you do that, you should get approximately 94. What do? We observe 96. 94 is here. We're saying we're going to reject. If it's over here, is it over there? So, again, we still fail to reject. So the p-value is just the same thing that we used up there, p norm 96, 115 over 6, and we don't multiply by 2 because it's only one tail. So, exactly right. Ruby. So, what is the power? So, in our example, we found the mean was 96, right? So our best estimate of what the population mean for all of the here students is what? 96. That's our best guess. So now we have the null hypothesis, right? That said that we have a mean of 100. And we had our critical value. For the one-tailed test, it was 94 point something. I'll just put point X. Now, if we want to know what the power is for a specific alternative, let's imagine, so here was 96, right? If we really had a distribution where the mean was 96 and we had the same standard deviation, well, that would look, it's going to be hard. Like that, right? See if I can get a different color. What's going on with this? Now the power, can someone remind me what the power is? Not correctly failing to reject, it's correctly rejecting. Power is the probability that we will correctly reject. Now notice, we have a critical value from the null hypothesis, right? That was this. So we will always reject if it's above this. So the probability that we will fail to reject if the true mean is 96 is just all of this jazz in here, right? The power, that's this. If we had a two-tailed hypothesis, we'd also have some point over here to add in. But right now, this is just a one-tailed hypothesis, right? Okay, so we have our specific alternative. All we need to do is use the critical values that we already got for the null. Then, p-norm, L-crit, that's just the lower critical value that I previously computed. L-crit. Now, notice here instead of 100, I'm saying 96. Right? Which is the mean that I'm predicting in my specific alternative hypothesis. And I'm using exactly the same standard deviation that I was using before. So, can anyone tell me what that is? So you just calculate the power. So, you know everything that you need to know for finding critical values for a z-test, for finding the p-values for some observation, for calculating power, which also means that you know how to calculate something else. You know the power, what else can you calculate? Beta.